previously with lenses, we had talked about a graphical method of finding the distance of the image of an object projected through a lens. We saw that there are some problems with that method, which we call the ray tracing method. And the problems were that there's a lot of human error with the thickness of the pencil line and not drawing lines perfectly parallel to the principal axis, or not drawing lines perfectly through the center of the lens. So today we're going to look at a mathematical method of finding the image distance instead, one that's a bit more precise or accurate than what we had before. So here's our mathematical equation, which is the thin lens equation. It says that 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. Now I can also calculate the magnification of the image itself as well, using the equation that the image height divided by the object height is the magnification. So how many times larger is the image than the object height? We also have that there's a ratio of the opposite of the image distance divided by the object distance. So we can get the magnification either based on the heights of the objects themselves, or we can get the magnification based on the distance from the lens, the image distance and the object distance. But the negative is there because sometimes the image itself is flipped upside down, as we've seen in the past. And so that's actually a negative magnification when the image is upside down from the object. So let's look at some sign conventions. For us, we're only dealing with converging lenses here for this first part. And so for a converging lens, the focal length is positive. Of course, then for a diverging lens, it would be negative. But we're only going to work with converging lenses for now. So positive focal lengths at all times. The object distance is going to be positive if the object is on the same side as the light source. It's going to be negative if it's on the opposite side of the light source. And so for most of everything that we do here, we're going to have a positive object distance. Very seldom do you ever have a negative object distance. If we look at the diagram, if the object is over here, it would be positive, and if the object would be over here, it would be negative. Well, we always draw our objects on this side here, on the same side that the light is coming from. The image distance is the opposite. The image is positive if it's on the other side that the light source is. We call this a real image. So if the image is somewhere over here on this side, we say that it is positive, and we call this a real image. If the image would be over on this side, it would be negative, and we call this a virtual image. So what's the difference between a real and a virtual image? A real image can really be projected onto a screen. So if I take a screen like a movie projector screen and place it on this side, and we get an actual image of an arrow. So if I have an arrow over here and I have my lens, and the actual image is projected onto a screen on this side, well, then it's a real image. If it were on this side, you could not project it onto an actual screen. So if the image appears to be over here, then you could not project it onto a screen, and it would be considered a virtual image. This is similar to looking in a mirror. I know it's not a lens, but it's kind of that same idea. When you look into a mirror, it looks like there's an image of you behind the mirror. But if I take a movie projector screen and put it behind the mirror, I don't get an image projected onto it. So it's a virtual thing. It appears to be behind the mirror, but it's not really there. There's no image, there's no person or image really behind the mirror. So what we're referring to with real versus virtual is, can we project that image onto a screen? If the answer is yes, it's real. If no, then it's virtual. Height, we can have positive and negative as well. Height is positive if it's right side up, and height is negative if it's upside down. So for most of our circumstances, at least to start out, our objects will typically be positive because they're usually right side up, and our images for the most part right now have been upside down. For all of our images so far, they've been negative. So again, we can use the thin lens equation to solve for where this image is located, how far it is located from the lens itself. It's more precise and accurate, and we have to be careful about our signs. For the most part, we'll have positive focal lengths because we'll be using converging lenses. We'll pretty much have positive object distances because we'll just have all our objects on this side of the screen. So positive object distance over here, negative object distance over here. And we'll typically have positive image distances as well, because most of our images will be on the right-hand side of the screen. And our heights so far have been upside down, so most times they've been negative.